Hello, everyone. My name is Rodrigo, and I'm a software engineer at Facebook on our server product infrastructure team. Today, I'm here to talk about live queries, a new way of doing real-time updates with GraphQL. So what to expect today? First, I'm going to talk about what is a live query. We've been dropping this term all throughout the conference, but no one really knows what they are, so we'll get into that. Then we'll talk about why we believe in the value of live queries. Next, we'll talk about subscriptions and live queries. Rob touched on this in his talk yesterday a little. These things both occupy the real-time update space, so we want to know how are they similar, how are they different. And at the very end, I'm going to talk about how do we go about actually implementing live queries, which I think as an infrastructure-oriented person myself, which is probably a little odd for this audience, that's what I'm really into. So let's dive right into it. So what is a live query? Let's start with a regular query, which should look familiar. I'm borrowing from Rob's example of a Game of Thrones world that we live in. We have a house with a name, words, and bannerman. Suppose we're building an application that that uses this information, and we would like to keep this information updated real time in our application. How could we do that? What if all it took was adding a simple @live annotation to the query, as shown here? Sorry, @live directive. You could push play, and then GraphQL would take care of keeping the results updated with the latest value. And it would look just like this. That's really all there is to a live query. The desire with live queries in this client-driven development fashion is make it easy, really easy for product developers to add a simple annotation that expresses their intent in receiving updates for their data. In the same way that GraphQL lets you specify an intent for data without worrying about how it is produced for you, with live queries, we want to allow developers to express the intent in keeping data updated and then leave it up to GraphQL to figure out how to do that for you. And we will talk about those approaches later. I should clarify, what you're seeing right now isn't real. It isn't really a live query. I just hacked a directive together in a local build. But you could be a live query engine yourself if you opened up GraphQL and just push play a bunch of times. So why live queries? Subscriptions are awesome, and they already exist. You can use them right now for yourself. Do we really need another way of doing real-time updates? Let's work together through an example that I hope will illustrate why live queries are valuable and why we are pursuing them. So back to our original example, Game of Thrones application, showing using this query. In our application, we have a mutation called pledge bannerman. Similar to yesterday, I've enhanced it a little bit such that we give the bannerman names, and we track a list of the bannermen. So we want our application to be able to respond to these mutations. How can we achieve that? One naive solution is polling. It's nice, and it's dead simple. All you need is a timer loop, and that's basically it. There's no additional infrastructure required to build liveness like this. The problem is it's inefficient. If you poll more frequently than your data changes, you're doing a lot of wasted work. We can do better than polling. Instead of constantly asking for updates, we can push updates to clients. We can let our servers notify us when things have changed. In this solution space, we have subscriptions and live queries, and I would like to take a look at subscriptions first. So with subscriptions, we could create a bannerman pledged subscription to notify us of new bannermen. On the server, we would extend our pledge bannerman mutation to fire some kind of event to notify that a bannerman was added to a house, that was pledged to a house, and then all the subscribers would be notified of that change. And so whenever a bannerman is pledged, we receive an update payload with the bannerman name and the list of bannermen. Now let's say our application grows, our world gets a little more interesting, and there are more kinds of mutations, more kinds of events that can take place. Imagine how Stark gets invited to a wedding, and all of a sudden it's like, oops, there go all our bannermen. Season 7 could roll around, and winter is here, and they see it fit to update their words. All of the Dickons in the world could realize that they have really silly names, and they want to change them. There's a tournament to find who your best bannermen are, and now the list is ordered in some way. We want to react to all of these mutations, and all of them affect fields in fairly straightforward ways, so you can easily create a matching subscription for each mutation. So far, so good. Now imagine we extended our application and added a description field to our houses. And this description field could look a little like this for House Stark. House Stark, whose words are, winter is coming, it is a barely existent house with no bannermen, because our application is fresh still. For the sake of this example, assume that as we compute this field server-side, maybe for translation, or maybe to control the rendering, who knows. The important thing I want to highlight here is this description field depends on three other fields right now. We are displaying the house name, its words, and something to do with the bannerman for the house. How do we keep this newly added, this computed description field updated? One option would be to reuse our previous existing subscription call. We simply add the description field to be included to the payload, and then whenever a bannerman is pledged, the description will update. This works, but it only covers a single mutation type so far. We could go and find all of the subscription queries that are relevant to the description being updated, but now you're adding this field all over the place in subscriptions that probably shouldn't be concerned about that field if that's not directly what the subscription is for. So it feels a little ugly. Another option would be to create a description changed subscription call all by its own. You could reuse the events that you added before for your other subscription types and have a subscription that reacts to many different kinds of events. Or you could create a new event type just for this new subscription call, and then instrument all of your existing mutators or wherever your data changes to fire that event. Regardless, the key thing here is that someone, a developer, has to trace down what are all the places that could affect my description and make sure that those are instrumented properly. And as your application grows, you need to keep those mappings updated and correct. This is fine if you've got simple dependencies. Even what I've got here is like a very simple, somewhat contrived example. You have 3 fields. Who's going to mess that up? I mean, people mess that up. But as those dependencies grow more complex, so does the burden on your developers. For fields that are really complex, it may simply be impossible for any one person on your team or any one person to track down all of the places that can to track down all the places that can affect the data that changes this field. And this, I think, is where live queries really come in. Imagine we had a server that could figure out by itself what data is relevant to your query and automatically update and push new responses for you when that data changes. If we could annotate a query to express our interest in keeping the result updated and then let GraphQL do the hard part, product developers don't have to worry about tracking dependencies, adding events, maintaining subscriptions, all that work. This makes it easier for product developers to experiment and iterate. This is in line with our client-driven philosophy. Now, mind you, though you've made your product developers' life easier, you now have the problem of building a reactive backend to power your system, amongst other considerations. You've made your infrastructure engineers' lives a lot harder. So there's trade-offs. Having hopefully illustrated a case for live queries, I would like to take a look at the similarities and differences between subscriptions and live queries. I would first like to make the claim that subscriptions and live queries are interchangeable. They're effectively isomorphic with some caveats. Anything that you can build using subscriptions, you can build with live queries and vice versa, even though there will be tasks where one would be a lot more suitable than the other. The reason I make this claim is the relationship between state and events. You've seen this slide already, so I'll just go over it very briefly, but the idea is live queries are state-oriented. We are interested in seeing the state of our query update over time. Whereas subscriptions, they are event-oriented. We receive events, we execute some query when we get the event to update our application. With subscriptions, we can be notified that an event has occurred. Maybe some value was incremented by X. We apply it to our state. And this way, you can map a subscription to a live query-like behavior. With a live query, we could observe that at some point in time, a value changed and look back in time and infer, hey, an event probably happened here. You can't always do this. In those cases, maybe you can expose a list of events as part of your state. That's ugly. I'm not saying this is a great idea, but illustrating that these two things should be interchangeable. Another slide you have already seen. With both live queries and subscriptions, there are some shared requirements. You need some kind of streaming transport so that you can push updates. You need some kind of reactive API or language so that you can actually react to updates. With subscriptions, you need some kind of streaming or event system and to add domain-specific events. And the nice thing with subscriptions is you know not just that data changed, but why it changed, because it's part of the event. And you have fine control over when you publish the events. With live queries, you need a reactive data layer. This isn't the star is, it's not just a reactive database, just a reactive data layer. Whatever you query to produce your result has to be reactive. The benefit is you can, in theory, convert any existing query. You just annotate it. It shouldn't require server-side changes beyond building your initial infrastructure. And it has a nice property of if your live query server isn't doing so hot, you can fall back to polling because, again, you yourself can be the live query engine if you just push play a bunch. In situations where we must know some information about an event itself, I would claim subscriptions are a better fit. In cases where we only care about the state or we have complicated dependencies for our fields and it's impractical to manually subscribe to all the relevant events, live queries will be a better fit. In many cases, like this simple query that I'm showing you side by side, subscriptions versus live queries for keeping Bannerman updated, both live queries and subscriptions should behave the same. There's a lot of middle ground where either would be suitable. So picking one in these scenarios becomes a judgment call. Now the fun stuff. Let's talk about implementing live queries. One perfectly valid implementation is polling. A live query can be modeled as a regular GraphQL query if you polled it infinitely fast. Because of this, polling is a reasonable enough way to implement them. And if you want to get experimenting with how would people behave when using our application if we expose live queries, this is a perfectly good way to measure that without having to build out the whole infrastructure for it. With live queries, you can do polling on the client, same as you would for regular queries. A nice property is because you only express the intent at the GraphQL layer, the server could do the polling for you. It can save some client-side resources and do optimizations like better scheduling or batching of queries. But as before, polling can be inefficient. We can do better. I would contend that a better implementation would involve reactive data stores. When you run a query, the server would implicitly determine what the dependencies are, observe the relevant data, and keep the result updated for you. Some existing tools that you could use are things like Meteor, Firebase, and RethinkDB, to name a few. On the slide, you can see a RethinkDB query in action. It's got a list of players, events coming in. and the top scores. And you can imagine, instead of rendering a bit of UI, you render a JSON response of a GraphQL query. Small and simple applications, like for our Game of Thrones example, could conceivably be built using these existing tools that I'm talking about right now, without very major hassle, I would think. Although with scale and complexity come challenges. That's the fun stuff. And there are also challenges involved in taking existing infrastructure and making it reactive. A basic diagram of what a live query engine could look like is a little like this. You have a client which has a bidirectional connection to a stateful GraphQL server. Again, it has to be stateful because something needs to maintain the connections and be able to push up updates. And then the server has a bidirectional connection to a reactive data store so that the data store can push updates to the server when data changes, and then the server can push updates to your clients. Imagine instead we started with an architecture like this, where we have a stateless request-response GraphQL server. Much like we do at Facebook, we use PHP. It is stateless request-response. With something like this alone, you couldn't implement either subscriptions or live queries. You need some stateful system for your connections and pushing updates. If your code base is large enough, rewriting your server to be stateful might not be an option. As much as many people would love to rewrite all of our PHP code base and literally anything else, that's just not going to happen anytime soon, right? So we need some way to work around it. And I would say not all hope is lost, because instead you can add a stateful server to the mix so that you can get these live query semantics without having to convert all of your infrastructure. And the diagram now looks a little like this. And let me walk you through the interaction model. So now you have a client with a GraphQL query that's annotated as a live query. We submit that as a request to our stateful server, which then passes it down to the stateless GraphQL server. The stateless GraphQL server can compute the response for your query. This is so far exactly the same as if your client talked straight to your stateless server before. Now, the special thing that the stateless GraphQL server does this time is, in addition to just computing your result, it keeps track of what data fetches were made during the request. So if we're rendering our initial Game of Thrones query for House Stark, perhaps we have some internal ORM or API that lets us say, hey, fetch a house with name Stark from this backend. After the response is computed and we have our response on our list of dependencies, we return to the stateful server this pair. We return the response and a list of dependencies. The response we send back to the client, as we would have normally for any regular request. But now the stateful server holds on to our list of dependencies. The stateful server can now use those dependencies to observe data by creating some subscription against the reactive data store so that it can be notified when changes happen. So now later in time, we're doing our mutations, and we mutate some property of House Stark. Because we had previously accessed it during our request, we are observing it. Our reactive data store can notify us, hey, we know you're observing this data. It changed. The stateful server gets the message. It goes and recomputes the query you previously had to get the latest state. It also gets the new dependencies in case they change, sends the response back to the client, keeps the dependencies, alters what it observes as necessary, and so on. That's the very basic premise of how we can do live queries in a system that starts off as stateless request response. Nothing in life comes free. There are challenges with doing systems like this. And there's a couple problems in particular that we've had to deal with that I would like to highlight. This is by no means a comprehensive list. It gets pretty long. But these are some of the things that I found most interesting and I hold near and dear to me that I wanted to discuss. Over-observing is one of the problems we run into. In your stateless request-response web stack, you can easily end up overfetching data. By this, I mean, if we go back to the idea that we have some API that lets us fetch data for House Stark, or we're trying to fetch data for House Stark. One way to do it could be just have your engineers write raw SQL queries or whatever your data backend is. That gets kind of ugly fairly fast with scale. Instead, you can have other nicer APIs, more object-oriented, so that we can say, hey, let's load House Stark from our backend so that we can use it in our request. One thing that this may end up doing is that it loads all of the fields in House Stark. It might load the entire row and pretend that we had more fields than just the ones I used for the query. Now you have the problem where the granularity of the data you're observing is at the object level. We're observing all of the properties of House Stark. If one of the properties changes that wasn't used directly for the computation of our result, imagine House Stark had a date when it was founded. I don't know how that would change. This is a terrible example. But suppose there was some other property that you weren't using in your computation, and that changed. Because you're working in a dynamic code base and you can't statically determine these were precisely the things that we need to observe, you run the risk of re-executing your query more frequently than you have to. This could also happen if during your request, maybe you had additional logging, you're computing features for some ranking thing, and you load a little bit more data just to pass it along to your learning backend. This wasn't meaningful to the result itself, but again, you fetched it, and we have to be careful and listen to it, listen to those changes. So unless you have some surefire way to identify precisely what the data that was used in computing your response was, you risk these kinds of updates. In instances like this, one thing that you can do is turn to dynamic analysis to build a model for what kind of updates are relevant and what kind of updates aren't. So you could see that if you get updates that change the house name field, and those change the result of the query, OK, these are probably relevant. If you get updates that change some other field that don't change the result, you can eventually start building some kind of statistical model for which updates matter, which updates don't. What I'm describing is roughly kind of also like how a spam filter works. You can take a look at user behavior, try to figure out what's meaningful to them and what isn't. And this now leads into interesting discussions of optimizing trade-offs between the correctness of your result, how often do you respond to changes that are meaningful versus changes that aren't, and the cost of running your live query. On one end of the spectrum, you can play it really safe and respond to all of the updates. On the other end of the spectrum, you respond to none of the updates, and your application never updates, so that kind of defeats the purpose, but it's as cheap as it gets. Opposite problem to over-observing would be the problem of missing data dependencies. Because we can only figure out what we need to subscribe to on the basis of what calls were made into backends during our request, if we don't make those calls to a backend, we may miss that data dependency. And specifically, an example here is caching. You may have some computed cached value that you may put in memcache or something like that. And you go to memcache, you fetch some key. If the value is there, you just return the value straight up from whatever your cache was. Otherwise, you go and compute it from your raw data sources. In the cases where we hit the cache and we don't happen to have a reactive cache, we will miss what the underlying data should have been. These problems aren't as easy to solve. Making your cache reactive is one option, but that takes work. You can enforce that you don't do caching for things that you care about keeping alive, but then that introduces its own set of trade-offs. I don't have a great solution for this yet. Similar to the problem of missing masked dependencies, it could also be the problem of missing dependencies. You can imagine if you're at a large enough company that you have a bunch of microservices, different backends, all sorts of things, not all of which you can make reactive in one go. And so you might live in a partial state where you can react to some kind of data changes automatically, but not to others. This creates issues for developers because now you don't know up front, is your live query going to work? You need to have some additional tooling for them to be able to figure out, if I made this thing a live query, how well does it work as a live query? And then it also makes debugging harder because if your live query isn't updating, it can be pretty tricky to figure out why it didn't update. I'm not going to pretend that debugging subscription systems is easy, but in a sense, you have a good mental model of you take an action, it publishes an event, the event propagates through a system, and then you expect it to propagate to subscribers. You have a somewhat linear mental model of how things flow. With live queries, you start from the opposite end of the spectrum where something didn't update, and if you couldn't manually figure out what all of the dependencies were to build a subscription version of your query, you're not going to have much luck working backwards and try to figure out what kind of data change didn't we react to. So that's a short of some of the problems we've encountered. I'm sure if all of you tried building live queries for your own systems, you would run into drastically different problems than we would. Now, having talked about what live queries are and how they can be used, I hope you're as excited about them as I am. At Facebook, we strongly believe in open source. Open source is awesome. Sharing things with the community is great. And none of us would be here if it weren't for Facebook's commitment to open source. We've been talking about live queries for a little while now. They have matured a lot internally since we've started talking about them. But there are still many details that we are trying to figure out. So we're not ready just yet to say we're going to add live queries to the language. In a similar way that subscriptions took some time to really, for us to prove to ourselves that they were right and this was something that was valuable and useful, and we figured out the right way to expose them, I expect live queries will take a similar path. And I can't wait to bring them to you someday, hopefully. However, the concepts behind live queries are simple. There is really nothing stopping you from going out and adding a directive and trying to emulate this behavior yourself. And in fact, just this morning, I received an email from someone that had hacked together a live query backend using, using Meteor and RxJS. And I fully expect that a week from now, I'll get emails from like 5 competing GitHub projects of people having implemented their own live query backends. So thank you very much for having me here. Have a great time.